So we are very happy to have Alok Bandha from CMI visiting us for a long duration. He has kindly agreed to give a series of 3 lectures on the infrared issues, defining S matrices. Today is the first of those lectures. The other 2 lectures will be on Wednesday and Thursday. We will send out the details about those soon. So today we are very happy that he is going to talk to us about contradictions in the infrared.
Thank you. So this is roughly the sort of the 3 nodes of my talk over this week. So I'm going to discuss the issues regarding the definition of what is usually called the hard S matrix in gauge theories and gravity, and I will mostly focus on QED, but in the end, if I have time, we'll say a little bit about gravity also.
So these issues are already non-trivial in QE.
Yeah, in fact, yes, non-trivial, and I would say to a large extent, not completely set. I mean, to some extent, not settled also. So some of what I will say, which is related to using what we know are the good quantities in quantum field theory to kind of pin down this definition is some work which is in progress with Ashok. And then, as we will see, there is an interesting relationship between analyzing structure of such S matrices with asymptotic symmetries, and this is some never-ending, ongoing, infinitely ongoing project with SAD, and we can for every 3 steps we go backwards. But so anyway, so really there is no, I mean, everything that I will say which is settled is not my work. So there is a beautiful definition of a hard S matrix which is given by Schwartz, Buffy, and which I will review, which is a sort of state of the art I would say right now. But in my opinion, this also has some issues, and those are the issues we are trying to understand through computing actual physical quantities through this S matrix. So this is roughly the outline of my talk. So let me now first start with some. So for this lecture especially, I will only focus on massive scalar QED in 4 dimensions. The process that we will one canonical example we will keep in mind is a process where we have, for example, 2 photons. Which scatter and give us 1 electron and 1 positron, equal mass m. So I would just like to keep this in mind as a canonical example of where all these issues can be understood. So the fact that we take incoming states to be photons is simply just for simplicity, because all the IR issues in some sense can be sort of focused by looking at the asymptotic outgoing states only. So let me first give some outline of my lecture. So we review the standard arguments on why S matrix in QED is thick. Then we will see that how the source of the problem, which is where is the source of the problem, which was discovered by Kudish and Pradeep long back. Found the source of the problem. Roughly intuitively, the source of the problem was that when we do scattering theory, we always assume that the asymptotic states are free states. But when we have long-range interactions, then they are never free because you have a 1/r potential, and this particle, even classically these are never free if you just study trajectories of these particles. So Kulish and Pradeep realized that we should really not diagonalize the free Hamiltonian, but study ideal states of the full asymptotic Hamiltonian. This I will explain. But the definition of this asymptotic dynamics was a little bit problematic in the way they did it, and all the effort that happened after that in subsequent decades is to sort of make it more precise. And this is what was really effectively done by these 2 authors through what is called soft collinear effective field theory.
Can you please one, sorry?
Yeah.
I don't know the subject. NS, what is that? NS?
HONNESDOTTIR. So this is a paper that came out.
You're not spelling it out.
I don't know how to.
No, that's fine, that's fine. Because it's just so vaguely I know Scheller or something else.
No, Schwartz. This is Matthew
Oh, that's
Schwartz.
Schwartz.
This is Schwartz. Sorry.
Oh no, this is this work. Okay.
Yeah.
Now I understand. Oh, so it's as recent as that work.
Yes. This is very recent. 3 years.
Okay.
3 years back.
Okay.
And then through this, they what they really did is make the Kulish-Farhi proposal, as you will see, very precise, and this gave rise to what they call the hard S matrix. And the main contention of the hard S matrix is that when we compute this amplitude, for example, of some electron, positron with momentum p1 and electron with momentum p2, and I compute just this amplitude, and then I have a photon with some k1 velocity h1, k2 velocity. That just this thing is infrared finite. So,
But there is no claim that it obeys a unitarity.
there is no claim right now that it obeys the unitarity equation, although as we will discuss, formally it does in the sense that the asymptotic, they have not changed the asymptotic states themselves. So we just use the completeness that you would ordinarily use. And at that formal level, you could say that, you could say that it's unitary, but I agree that, all the detailed analysis of unitarity, in my opinion, has not been done yet. But there's also other problem with this S matrix, as we will see that, the main issue is that, okay, we define this, but how do we know that it's somehow gives the right physics? But in order to even ask this question, we should know what the right physics is. And the irony in QED is that for a long time, we have known how to capture right physics by plethora of observables, which are called infrared safe observables, which we could have computed just using good old S matrix. So this is something I will explain, that even though the S matrix is sick, there are observables you can compute which are infrared finite, which people use in collider physics also. So this is these are our data points. So whatever proposal we give for this, better be such that the answer we get for these observables should match with the answer we got for the Dyson S matrix. So that's the attitude we will take in this discussion also. And it turns out that this one claim done by mathematical quantum field theorists like Wald and many other quantum field theorists is that the way to make this more precise is to look at implementation of what are called asymptotic symmetry. So in the end, I will at least touch upon the way they think about these issues. Roughly, this is the outline.
And of course, you will say much more, but roughly is the idea that SRH is just obtained by cutting out the asymptotic states just to have some momenta which are hard enough.
No. That
much
would,
more sophisticated.
Yeah, it may be much more because we at least want, of course, as Shiraz just mentioned, we want it to be unitary, which we don't know, but we certainly want it to be Poincare invariant, for example. So we would like to avoid any explicit cutoffs and all.
Yes.
So this S matrix is really in that sense, defined at the level of the usual S matrix, that we are not putting explicit cutoff or anything. But you will see what happens. It really, you have to augment the dynamics in the far past and the far future. In this example, only the far future, which is the missing part of the usual S matrix, because we assume that these particles are free when they are not. So we really have to take that into account and just follow the nose in some sense. But doing that requires some choices, and these choices somehow get crystallized with the development of this subject.
What I meant was, if you have to worry about photon exchange, etc.
Yes.
You just, you say, I'm not going to keep track of photons when they get arbitrary.
I will come to that. So
Okay, fine.
that is a part of the observables. Yeah, but those are
Sorry.
Yeah. So maybe it's a So let me first tell you what this. So maybe I should put one prime here, which is IR3 for observables. So first I will just quickly discuss what the issue is, and then explain how this strange situation that S matrix is ill-defined, but we can have many observables. One of them Sandeep just mentioned.
Sorry, hello. Yeah, restricted to massive QED so that the theory is free with the IR.
Exactly. Yeah. So otherwise we will also have collinear singularities which we have to worry about. Is that what you are asking?
I was thinking that the coupling would keep, if it was massless QED,
Yeah, it will keep running. Keep running,
all
which
the
we
way
want to
down.
avoid.
And
Yes,
that will introduce new costs.
Yeah, exactly. Yeah. So I mean, we will discuss more. I mean, there, the one of the interesting thing about Schwartz and Hoff's work is also that it supposedly can be applied even to theories like massless QED, which has collinear divergences also, and then there are other IR issues with RG running. So, but we will stick to this. Okay, so let me first tell you quickly what the IR catastrophe is. I think most of you know, so I will go into it. I mean, it's very elementary. Please, let me, just keep it, or ask me questions if I am not very clear about this thing. So let's just consider this process again, and let's consider it at one loop. The same process at one loop, and so we look at. Let's consider a diagram like this, which is the following diagram. So we have. So I just call it T1 plus for the positive one and minus here. And then let's just focus on this. So obviously, I think many of you would have seen that this. So when you have photon running around the loop and we have to integrate over this photon momenta, then this loop integration gives us an IR divergence. And the easiest way to see this is to just focus on the integration region for L, which is such that mod L is much less than the center of mass energy. Let's just call it S or E. And so if you just compute this loop in this case, then you see that this loop turns out to be equal to, I will just write it as a, so I'm just looking at this loop right now, nothing else, just this loop. So everything apart from this loop is a 3-level S matrix. So I will just call it, so let's call this A4 one loop. And so I'm writing it as this infrared contribution times A43 plus the rest. So the rest would be where the photons running a finite momentum. Okay, so that is an extra one loop contribution, which we are right now, just for the sake of the discussion, not worried about. And so if I take my L momenta to be much less than the center of mass energy, the center of mass.
Sorry, just to answer, A40 is when you don't have that loop.
Yeah, just 3 level, yeah, exactly.
Thank you.
And so then I just recompute and we get in the low L limit, we just get this stuff and A43. So that's the contribution that I get if I take my loop momenta to be much smaller than the momenta of the particle and mass of the electron, for example.
So in 5 dimensions and higher, this would be good.
This will be no problem. Exactly. And now this one you can do either, you can of course immediately check that this one is a log divergence. So if you put 0 here, this is infinite integral. So you have to, the best way we can do naively is to put some cutoff, let's just call it delta. And then we, so this is going to give us some divergent contribution in the delta going to 0 limit. So roughly this will give us log E by delta. And so this is a divergent integral as it stands. Without cutoff, we cannot make it well defined. So now what Weinberg in his classical paper showed is that, so as you see, what is happening is that this soft photon kind of decouple. This loop decouples. So this whole process can be thought of as this thing multiplied with the tree-level amplitude. And what Weinberg showed is that this will be true if you add arbitrary number of soft photons. In other words, if you have, you start adding more and more soft photons, they all kind of factorize and rearrange themselves into an exponent. So let me just write that answer that he provided.
So you sum the series of ladders.
Just some series of all ladders and cross ladders. And you have to be just careful with the only combinatories because yes.
There could be non-ladder diagrams where photons are also soft. Sorry, I don't know.
No. So the point is that that if this, that's a really important point. That if this photon was touching the internal line, then there will be no divergence. Because the divergence is coming because you have a pole in the propagator. Because P1 square and P2 square were M square. So which is why we get. So only higher divergence will come from low L photons if these photons are touching the external legs only.
Okay, sorry.
Yeah, please.
But can't you have external legs, but the photon which gets emitted from the first top leg first reaches the bottom leg later than
Yeah, cross ladder, exactly.
Those are also called.
Yeah, absolutely.
There's not just a standard bubble.
Not
And not large N.
Not large N.
Fine.
Everything.
Okay,
So that's why we have to be careful with the combinatory. And of course, one thing is that we have to take into account the fact that the helicity of the photon can be both plus and minus, and the photon could be running this way or this way. So all these factors we have to consider, and then Weinberg showed that the exponent gets exponentiated, and the final result looks as
Basically, the meaning of this pairwise interaction is that the asymptotic particle moves in the electromagnetic field generated by the.
Yeah, exactly. So just to say what which is saying a little bit more, that in Coulombic interaction, as you would know, that if I just compute xt classically, then it will asymptotically as t goes to infinity, it will go as some Vt plus c log of. But this term comes because we have a 1 by r potential. So it is this that is messing up the freeness of the particle at large times, which is ultimately responsible for this.
Any reduced power law, like in higher dimensions.
Will not cause this. Yes, exactly. So actually we can connect this, if you do one-line formulation of Q of t, you can see that from this, directly from here we get this. Right?
Sorry, are these the same diagrams you would some of the Eikenhower approximation?
Yeah.
Okay, so that makes nothing to
Exactly.
changes the classic.
Yes, exactly. So actually that's we will come to that also later. That this is really, in fact, that's one of the big motivation to do behind soft development of this subject is to treat soft emission as Eikenhower the scattering.
What is XT?
No, I was just explaining on a weak point that if I just take a Coulombic interaction 1 by r in classical dynamics, just Newtonian, and then you just study the equation of motion of a particle with charge q, then you see that at late times, if you solve the equation, you get this solution. I mean, of course, plus order to the 0 terms. Yeah. So now this we can exponentiate, and then this answer can be written as Weinberg showed as follows. So the 4-point amplitude we are writing can be written as when I put plus here, I just mean plus I epsilon.
But other massless things, those who continue immediate forces even at later, right?
Say that again.
They had massless particles, other massless particles.
Yeah, any other massless
So
particle.
those would add to these ladder type diagram. We will this pairwise approximation would break down.
Even if you have other massless spectrum in the theory, is what you're saying? Or?
I mean, here the massless particles are non-interacting. But let's say you had.
That's a great point. If you have blue one,
massless.
absolutely. If you have blue now, okay. So then also it's interesting. So if you have a graviton, then you may think that okay, I have a line like this, for example.
That or even connecting to the other massless, other asymptotic line.
Exactly.
So it's like 3 set.
Exactly. But now the point is that what happens is that in gravity, this vertex is proportional to the stress tensor. So in gravity, these don't contribute, but in gluon they do. So in gluon there is no such nice exponentiation, but there is a variant of, there is a Catani, others have written down some exponent of exponential where you have to cluster all these diagrams in a careful way. But that remains formal. But it is written, it has been written.
There isn't Shiraz's point valid with the coupling. I mean,
Yeah, there is also that. Absolutely.
Absolutely.
Yeah.
For instance,
We are assuming somehow that when we do, Shiraz, I think, they have said that QCD scattering, we are assuming we are above the QCD scale. So we are really doing perturbative QCD. So we are, I don't see that what.
But we could talk about it later. But I was thinking, even for the case of something that will eventually flow to, let's say, n equals 4 angle, some non-trivial conformal field theory.
Yes.
It feels like you need to put in information about that conformal fixed point to get this thing right. Like at the moment, you're looking at a theory which in the long distance limit becomes classical.
Yes.
And therefore, you can get away with basically classical dressing,
Yes.
which is what this iconology
Yes, exactly.
It feels like when you're flowing to a non-trivial conformal field theory,
Yes.
you'll have to do more. And there are all these issues about S matrices not existing and so on. So
Yeah.
we have to encounter all.
Yeah, so maybe we'll discuss a bit, maybe after the third lecture, about how, at least one of the things that Schwartz and Hofi are saying is that how for n equal 4 super young mills,
Yeah.
perturbative n equal 3 can.
Not now.
Yeah.
In the infrared free non-linear theories, the issue is that these coupling constants would go to 0. That's why you can ignore that. Is that
In this massive case, it's
in the Gluonic case? Let's say.
But in the gluonic case also we are looking at the processes only above the QCD scale. But I think Shiraz is saying that even then.
the infrared free would be very much like having massless tuning.
Exactly. Yeah.
And there again, you're going to have issues.
Exactly.
The coupling runs to 0 with logarithmic.
Yeah.
So there are going to be all kinds of things.
Yeah.
But, just one question: if we did what Sandeep wanted, was suggesting at some point, was counterfactualing at some point, which is these ladder diagrams which are planar, would this exponential have been replaced by like a geometric series?
I think so. I mean here, I mean there are few facts that combine combinatorially that you could have crossed, and also the fact that you have, you have 1 by 2 to the n coming from the fact that a photon could be running both ways. So I think all these factors somehow conspire to give an exponent.
Yeah.
That one is.
And these planar graphs feel like it's a geometric series.
Yeah, it has to be. It cannot be exponential.
Yeah.
So, a technical question: given that the answer is so simple, is
Yeah.
there a very simple reason for this a priori expect this exponential?
Yeah. The reason lies in the soft factorization theory.
No, but I mean, from the diagram point of view, is there like an operator which you just do multiple times?
I think so. You are right. So absolutely. I mean, the point is that you basically don't look at. Yeah, you don't look at the particle. You have to dress it somehow to cancel this. I think that's what you are saying. That dress particle will have a free trajectory. Is that what you are asking?
I thought it was a technical question, just to the diagram question about the diagrams.
So you are saying that can I cancel?
Way to see that these diagonals and cross ladders would generate some exponential effect.
Yeah, I mean it's.
Diagrams.
Yeah, it's just.
I mean, as you said, there's some combinatorial factors
Yeah,
conspiring.
maybe I'll say one way that Ashok explained this is that, so this is I'm explaining the way Weinberg did it, it's a classical argument, but there's another way to do it, which is to always break a photon propagator into, this Grammarian technique, where what you do is you break a photon propagator. For example, if you take, in a case, say eta mu by k squared, then you break it into eta mu minus k mu by k squared plus k mu by k squared. And this is what is called the K photon in the Grammarian literature. And the statement is that, so this is some gauge split, right? I mean, physical propagator is only this for us. And you use this, then you can see that this one will never give you IR divergent contribution. And so then, from that perspective, this combinatorics become very simple in the sense that every time you have K propagator, you have factorization, but you have G, there is no factorization. I don't know if that helps. I mean, so there is probably a nicer way to do this than Weinberg. Because for Weinberg, you are right that one has to really see the combinatorics carefully, which includes all the ladder configurations, helicity photon trace, and also this direction of photon population. Yeah.
But can I suggest something? Sorry, I'm so out of field, it's obviously crazy.
No.
You should go ahead. Which is just using what you said about the whirl line and dressing. Suppose I did a calculation where I had external sources instead of the E plus and E minus,
Yes.
and I computed their interaction because the photons are exchanged. Where these are just sources, right?
Yes.
Then it's clear that the effect will be an exponential because you have J dot A and you're integrating A out.
Yes.
And shouldn't the soft factors in that problem be the same as these? Because
I think so. They will be.
Yeah, so then that will answer why it should be exponential. Okay.
Okay.
Just,
Yeah.
Okay, sorry, but I mean, you could
No,
match that
yeah.
with this.
One technical question now.
Yeah.
Is it known what this factor is in ADS?
With ADS, we don't have IR divergence, we have a box anyway. But you mean in the Mellin space somehow? In the Mellin, there may be some factorization in the there may be some soft limit. But in general ADS,
But if I think of interaction in ADS as some happening in some place, and then there is propagation all the way to the boundary, but now that propagation is not going to be because of the process.
yeah.
Then it should.
Yeah. But somehow we are that why is this happening? This is happening because we are able to take L square to be much less than P1 dot N. But there L square is bounded by 1 by R square. I mean,
But it would still be much less than that.
yeah. So if your kinematics of P1, P2 is large enough, I think then it would be similar because then you are effectively in flat space.
Well, but
Right.
the propagation is over long distance.
Yeah.
It sees ADS.
Yeah. But I think that the scattering is happening in a region where it doesn't know about ADS somehow. I mean,
Yes.
So
This physics is about not and that region. Right? This is about once you go out of that.
Yeah. So you are saying that look here, I put a delta here. I mean, let's just look at this one. I put a delta is 1 by R, you are saying.
Yeah.
Yeah, I would agree. At that level, certainly it will make sense. But then your point is because that delta is physical, we have no reason to worry about that S matrix. Right? It's just some large exponent, but finite, always finite. So the issues are not severe. I mean,
I think Abhijit is asking for correction to the bulk point limit factors.
from this exponent you have.
Yeah, it's very interesting.
Yeah, I see.
Because the bulk point limit, in the bulk point limit, there's some prefactor, kinematical prefactor times an S matrix.
Yes.
And the kinematic prefactor will get corrected by this kind of margin.
Yes.
So how do you connect the bulk pointing including these?
Yes.
Something very interesting.
Yeah. I think this may be even, the question may even be, we would be able to pose it once we understand this Schwartz construction. Because there, the idea is that you dress this with soft Wilson lines as we will explain. That may have a nice weight even in the case. Okay, so now this is, so this is what Weinberg showed, that that you can always completely factorize all the IR issues, and everything else you can just package it into what I've written here is A4 finite, and this integral is going from some cutoff to P. So it's a sec, it's a function of delta. So for of course we are always interpreting delta go to zero limit where this is infinite. And actually, if you compute this carefully, remember that this has some I epsilons, etc. So this is not manifestly real, except the I. I mean, this has both complex and imaginary and real pieces. And it turns out, so we can write this as. So let me write this as exponential of 2 real phi 1 2. Sorry, real phi 1 2 imaginary phi 1 2. Phi 1 2 being just this stuff here. And then you can check that this part in the limit delta going to 0, this thing goes to minus infinity. And so the S matrix vanishes, the amplitude vanishes in the delta going to 0 limit. So as delta goes to 0.
So I missed something. So that object with the delta lower cutoff is called phi 1 2.
Yeah.
And then what did you say there?
So so this will go as log delta.
Yes.
And then log delta will go as delta goes to 0 as minus infinity.
Yes.
So that means this S matrix is going to 0,
Yes.
which physically makes sense because we are saying that there is always a finite probability to emit any number of soft photons, but the total probability is 1. So of course, if you fix your configuration, external states, then it better be 0. Probability better be 0. So this is the infinite catastrophe that. Okay, so this was the very basic introduction to the basic problem that we want to face, even for such a simple S matrix. So now, but even then, even as Weinberg himself showed, and then developed by many others, that this shouldn't stop us, of course, from doing 3D, because we can define observables, even though S matrix.
Sorry,
Yeah.
Just help me separate the real and the imaginary. One of them comes only because there's an I epsilon.
Yeah, I think so. Yes, exactly.
Which one is the one that comes from the I epsilon? It's imaginary or real?
So the that's a good point. So this is So I think one way to do it is just break this into delta.
Right. So this integral is naively real.
Yeah.
But there's an I outside.
Yeah.
So therefore the imaginary part comes without the I epsilon.
Exactly.
And the real part comes because of the I epsilon.
Exactly. And one way to see it would be to just break this into.
Fine.
Yeah.
Excellent.
Yeah.
And so now these two have different physical interpretations then?
Yes, exactly. Because in the cross section, this will not play any role.
And that is the thing that captures this 1/r force?
This is the one that actually captures 1/r force.
Right. So
This is the one that captures the emission of
Yes,
the
yes, yes.
photon. Yeah, as we will see. So,
Yeah.
And that's what was not clear. Why the 1/r was given? Okay, so this.
so 1/r is kind of packaged here,
Now I
but
got
you know,
it.
in fact, yeah,
Yeah,
we
the
can further define the.
I got it. So it's actually just the on-shell emission that's
Yes,
coming up.
yes.
Okay, I'm now making. It's actually the lines not connecting back, but sort of going off. It is as an asymptotic state, right?
So you see that. So right now here there is no external. We have so in this process we have no external photon emission at all because you know we are only looking at this process. I'll explain that that this divergent phase can be split into, complex phase can be split into something which, as we will see, gets cancelled if you combine this process in cross section with process where photons are, as you will see now. So it's from here we can't necessarily interpret this as a real photon emission, but we can interpret it in the cross section computation. But this one we can certainly interpret as a simply coming from the shift.
So, but if it is coming from the epsilon, then wouldn't that have an interpretation of the cut then? So it could be interpreted as a real
Using unitarities.
Okay, thanks. Okay, good. Exactly. So you are, we say even more precisely actually that even here we can, because delta means we just cut it. So that's a photon emission. Okay, thanks. Yeah.
But they do on-shell basically.
Yeah, which means you just direct yeah. Yeah, we can just cut the propagator. That's how this exactly this will come. Okay, so now let me just give you some example of IRCF observables starting from Weinberg.
So, sorry, just to
Yes.
be totally clear. So if we were to just do classical physics as well as we could, we would get that imaginary part but not that real part. Something like that.
Exactly. I think this is what IRD has explored to greater degrees. So there are more tales, right, of what log. When I wrote it like this can be a little misleading because as she has shown that you can have terms which are of the type t log t by log t square by t. What are the tail terms? You have some subleading in log, right?
Log t by t.
Okay, log t to the m by t to the m plus 1, something like that.
And all of these are classical.
All of these are classical. Yeah. Okay, so now I give some examples starting from Weinberg. So Weinberg defined in the same paper where he showed this observable, which he calls sufficiently inclusive cross section. Actually, this was before Weinberg. This is log. This is this idea before Weinberg. And the basic idea is the following, that this is what his idea was, that okay, let's look at the process again. This is not
He's praising your presentation.
crazy.
Yes.
Abhijit is too kind.
Not with everyone.
So what basic idea of Weinberg to define this organometric, the idea was that okay, we have a detector, whenever we are measuring anything, we have a detector, but the detector has some resolution in the energy scale, let's say delta E. And so that means that this process could be emitting any number of photons, as long as the energy, total energy in these photons is less than or equal to delta E, these photons will remain unobserved. And so that means that when we compute cross section of this, it makes no sense to compute cross section of this amplitude because every detector has a threshold, and so we have to sum over all the final states with arbitrary number of photons with energy less than delta E. Of course, here only final states because the initial states, there's only 2 photons, nothing else in there. So you don't need anything in this case, more complexity. And also now this you can compute because this is very easy to compute. And this one is given by. So we want to. So I hope the process is clear. So now we look at. So let me define this observable. So this observable, we call it sigma SICS. we just define it. So this is defined as summation over all. I will explain. Soft. The definition of the sufficiently inclusive cross section. That we do a cross section, but usually we will not have this in the ordinary cross section. We just mod square. But here we trace over all the photons with energy less than delta E, which means you have to now trace over arbitrary number of photons because a photon can have arbitrary small energy. So if I fix delta E, I can have infinite number of photons. But they have to be soft, which means that we have to use this universal factorization for soft emission, which tells us that if I look at the 5-point amplitude with to any loop order, where your K1, K2, N2, P1, P2 plus 1 photon, let's say 1 photon with any momentum K1 prime, heredity H1, then we know that if you expand it in the energy of K1 prime, this looks like this is the plus terms which go as log of omega mod K1 prime. So this one, as you can see, possesses 1 by omega 1 prime, mod K1 prime. So this is the most dominant term in the infrared. And so what what Weinberg showed is that, okay, let's do this tracing our soft photons, which all factorized by this formula and this formula only. And then it turns out that now we can see what happens actually. Yeah.
So we look at this 5-point amplitude, and then just say what will you say on that?
Yeah, so I'm saying that if I have a 5-point amplitude to any loop order where I have 1 photon being emitted from in the outset, then if the photon frequency is much less than the momentum of the electrons, then you can do this expansion.
Okay.
And the expansion has the most dominant term, which goes as a pole in the frequency. And then there are higher order terms which will go as log, etc. But they are subleading in small term. So Weinberg's idea was that, okay, we trace over all the soft. By soft, he would mean all the photons where the dominant contribution coming only from the.
And just this is a tree level amplitude, or
No, this is a that's what at any loop. Yeah, exactly. And the reason is simply because this simply means that I have a process like this, and I'm only looking at emission from here or here. So it doesn't matter. It won't care about what happened here. So yeah. So now we use this in this trace formula, and you can immediately see what happened, because if I just give you one illustration, quick illustration of how to do this. So suppose I take one photon, then what we are saying pictorially is that we have a process like this. I emit one soft photon, so it could be emitted from one of the external nets. But then I'm tracing over it, so I have to connect it like this. So I'll get, so I will get an extra contribution which is of this type. But what is this contribution? This contribution is simply integral over the photon momentum, let me call it L, because I'm tracing over it. And then when I trace over the polarization, and if this momentum is P1 and this is say P2, then we will get P1 up to some factor P1 dot P2 by this guy, which is P1 dot L plus, or in this case minus, because one is that conjugated, P2 dot L. So we will get a term like this. So now you can imagine that if you
D4L or D3L?
1 by L square, sorry.
Sorry, I didn't understand.
One by L.
Because it's on shell.
On shell.
You've converted that D3L into.
Yeah. I could have written a D3L, exactly. Thank you. Yeah. So, yes. And so now what Weinberg showed is that now, but you have to somehow all possible any number of photons with total energy less than delta E, and that can trace because every soft photon is factorizing like this. It's again like this iconal thing that Shiraz also talked about, and then we get the following. We get a nice, nice result, which is the following that the sigma SICS is exponential 2 real 512, and then we get exponential I minus I actually this as Chirag said, right? I mean, it has to be delta exponential. So we get. So let me write this. Sorry, I will just rewrite this a little bit. So let me write this with the integral delta to t, and then whatever was in the real part of the integral. Sorry, I wrote this. I mean, I hope it's clear what I mean. Yeah. And then here what we get is minus 2 from the tracing of soft modes. We get.
You're basically getting what you get from the I epsilon part, expanding that as delta function, right?
Exactly, it's the same thing, except that now here it turns out that because of the fact that one is tracing over the in and the out, the sign switches in the computation, and it goes from minus delta to whatever was the mass of the photon, because we are saying that soft photons are those with, of course, frequency much less than the mass of the photon. So we get this times real I. And then the mod A4 IR finite square, whatever was apart from this guy, that square remains as it is. And so you can immediately check that this.
So where is delta E? Delta E.
But this E is the sorry, what am I saying? Sorry, upon this. That's not M, that's delta E. Yeah, thanks, fine. And so now you see that these two.
That's the imaginary.
No, in the cross section, imaginary part will drop off. This is mod square.
Right.
Yeah.
Sorry.
So then this just gives us 2 delta E to E, real part of I. So this is the first example of the IR finite observable, which is parameterized by delta. So now delta disappeared. So that's why it's infrared finite. We can take delta go to 0 limit, but it depends on the resolution scale of the detector.
I'm sorry, I missed where you got the factor of 2.
Yeah.
Yeah. You have to work it out, just saying.
Yeah, you will get it.
Yeah, no, I got it.
Mod A4 square.
No,
On one side it's that, but from on this side where it comes from.
So I would just say okay.
Meaning, if you take this guy and mod square it, you get that.
Yeah.
But he was
why
saying,
did we get a 2?
why did you get a 2 from the software? It's probably I can just put it.
No, that's a very good point. I mean, there should be a way to see it. I will check this here.
Yeah.
Sally, do you remember? She is usually my go-to person in these IR computations. Okay.
What is the initials SIC inclusive cross section?
Sufficiently inclusive.
Sufficiently.
Yeah. So we are not doing total inclusive.
Yeah.
We are not totally agnostic about the outlet, just sufficiently inclusive.
So now the divergence in delta has been replaced by a divergence in
Exactly, in delta E. Delta E. So this is for several reasons. This is not a satisfactory. I will come back to this point. This is not a entirely satisfactory observable. But let me give an example of few more observables which are interesting in their own right and more baffling that we have no asymmetric but so many different observables. So another example is, let me just call it KMC observables, which are now.
Isn't the bottom line is that you just ask a correctly experimentally posed question and you get right answer.
Yeah,
That's how
that is the motivation. That was the motivation.
When I took the course in the.
Yeah, this is exactly. Yeah, exactly.
Just ask a question and experiment just would actually.
Yeah, exactly. But you know, but there is there are some yeah, I was come back. I'll come back to this more. But there are some issues here. For example, momentum conservation is now not sharply implemented. So we are saying that we can commit an error in momentum conservation up to delta E. And so this is not observable, which is a very good theoretical footing in that sense. So we are saying this is okay, but momenta are not sharply defined.
And maybe one more thing about this, that I feel, is that one of the really nice things about an S matrix is that it's completely fine-grained observable.
Exactly.
There's a basis of complete basis of states.
Exactly.
And therefore there's a unitarity relationship.
Yes. That we cannot even know. Yeah.
There's no S dagger S is equal to 1.
Yeah. So here we are saying that that's a really good point. Here what we are saying is that we can only think of QED as an open quantum system. We cannot think of it as a closed system because we have a detector outside. It is going to absorb some photons which we have no control over. And those are observable. So in that sense, this doesn't fit into our usual QFT. So in that sense, this is a little unsatisfactory. Now, let me tell you about these observables that are in vogue these days, which are called KMOC observables. So here, idea is the following. Then let's start with a coherent state for electron-positron pair, for example. So let's start with the ink state, which is.
Alok, could I ask before you?
Yeah.
If you try to do the same thing, just this cancellation for QCD, does that work?
No, because of the fact that I think two reasons. One is what the collinear singularities, which will not work like this. And in QCD, because of this extra IR divergence coming from Gluon coupling,
Yes.
just summing over final states
Does not.
does not work. There is a version, as you know, the KLN theorem, which says that if you somehow trace over all degenerate initial and final states.
I didn't even know.
So KLN theorem says that if you give me take a reference energy E naught, and then look at all states, all gluon states with energy E naught minus delta and E naught plus delta in the initial configuration and also in the final configuration, and trace over all of them. And then that is a higher finite quantity. But this physical is not interesting. What does it mean to trace over initial?
So the initial was needed because you are scattered. The initial states are also gluons.
Exactly. Or no, even if they're quarks.
Okay, but suppose I had to.
Yeah, even if they're quarks.
The initial states were also charged under this.
Charged under
Non-immediate.
Yeah, exactly. And actually, there is some this argument I'm not remembering very well. Schwarz's argument that actually, even though KLM proof looks complicated, if you really look at it, this proof is kind of trivial. If you sum over initial states, because what really plays a role is that it's not just that you have to account for degenerate initial and final state, but you have to include forward scattering to cancel the IR divergent contribution. So Schwarz and his student, they have shown that KLM theory in some sense very trivial. I mean, it's not a. So I mean, but this is my ignorance about QCD. Because I think QCD is held secret. KLM theorem. So
Sorry, something. Just to ask you.
Yeah.
Okay, this is not totally fine-grained, I agree, but it's an experimentally observable quantity, right?
Yeah.
So let me ask this. Are there no experimental implications of unitarity? If I just asked you, okay, you have this beautiful matrix, how would an experimentalist go and check it? There must be something there, right? So then, can we not, taking this moral, say, okay, let's phrase at least some consequence of unitarity in terms of IR safe.
One could. But there would be, I think what Alok will try is to hope for something even more. That there is a replacement of a fine-grained S matrix that obeys some replacement of S dagger.
Okay, that would be great, but I mean, I'm just saying otherwise,
I'm sure you could do it.
Yeah.
Okay, and sorry.
But Sandeep, I would say still, I mean, that these are not entirely satisfactory definition in this sense that we are somehow trading. We are also a little bit compromising with Lorentz invariance, Poincare invariance, because we are saying that okay, we can violate momentum conservation up to delta E. So I think that these are kind of telling us that generically in QFT, if you have massless particles, we cannot think of it as a closed system, which is taking us away from the usual paradigm of QFT. I would think so.
Okay, I mean,
so you are right that of course if you do any detector measurement, it is an open system anyway. But usually we can do more now in QFT. So.
Yeah. I agree. It would be great to have a completely fine-grained. I mean,
right.
Just to understand, I mean, don't mind. The last time I encountered this subject was when I took a course in the wonderful theory and I won't name the instructor who went on and on, but the thing I got out of it also then for QCD was you again define these jet observables. Right?
Exactly.
Again, which are physical. You ask what they actually measure in the collider experiment, and again it's IR safe. Right?
Exactly.
So, I mean, in the end, if you phrase it as a physical question, the theory returns a finite answer.
Yeah, I think, but in one issue is that even QCD, the one that you are talking about, these event shapes, they are slightly not defined like this. We can talk about that.
Okay,
There you have
don't
to,
do that.
yeah.
But this model is sort of correct, right? I mean,
Yeah, the model is kind of correct. Yeah, I mean, I agree that you are saying that. I mean, here the point is there a good theoretical basis, let's say, for these observables? That's the maybe one question.
okay.
Yeah. So let me give a different class of observables which don't depend on the resolution scale or anything.
Sorry.
Yeah.
But what would the analog of jet observables be for n equals 4? Would they be like these Maldacena-Hoffman kind of observables?
Yeah. Schwartz gave an example also in his paper.
It feels like it's Maldacena-Hoffman.
So Maldacena-Hoffman was this
Expectation value of
exactly.
operators.
That's the sphere at infinity, right?
Yeah.
So you get a distribution of energy, right?
Yeah.
That's exactly the that's event shape. Yeah. So let me define. So we take two. I mean, we have the let me call the phase space measure d mu to just not write all the energy factors also.
But just one more comment.
Yeah.
One more comment about this is that, one thing that makes at least me feel that something more exists is that people who do n equals 4 angles S matrix theory compute something, which is the S matrix, and they compute it by using dimensional regularization.
Yes.
Which regulates both UV and IR.
Yes.
And they compute and get very beautiful formulas.
Exactly.
So it feels like they're computing something.
Yes, exactly.
It's not clear what they are computing.
Exactly. I think that's the question.
I see. And so, just sorry, 1 minute. And so, in a sense, they are either throwing away or regulating the IR.
Yeah, they just do dimensional regularization, shut their eyes and compute. So both divergences get regulated, and they get very beautiful answers.
Yes.
With very beautiful properties.
Yes. Exactly.
So it doesn't feel like junk. So maybe the goal for us is to find out what it is that
In fact, I think if you look at Schwartz's paper about the superangle section, this is exactly the way he motivated. That we have this beautiful BDS answers, it works, but why it works? Is there IR manifestly IR finite rather than having cancellations? Is there manifestly IR finite definition?
And what they computed n equals 4 angles is completely fine, right?
Yeah.
Function of momenta of inquiry.
Exactly.
As unit.
As unit active, yes, I think it has unit.
Yes. So let me just give you this other observable. So let's take some Gaussian wave packet for one electron, one positron, and let's say they are separated by some impact parameter also. And now KMO asks the following question. Now you take any gauge invariant operator in your theory, for example, F mu nu or anything, and now you ask what is the expectation value of a gauge invariant operator in the out state. That would mean that what we have to compute is phi in S dagger let's just call it O hat out.
So this is like Maldacena-Hoffman.
This is exactly like Maldacena-Hoffman, exactly. And now, of course, in generically in quantum theory, this is going to be IR divergent because we are using IR divergent S matrix. But what this shows, which is still a little bit of a mystery, and now which is used.
I didn't understand. Sorry. Yeah. So you can compute. You take psi in.
So take some wave packet of electron positron in our mass scalar QED.
That top line is supposed to equal the bottom line, right? I mean, psi out is S psi.
Exactly.
Okay.
Exactly.
Fine.
So for example, we could compute net momentum transfer, like an impulse, for example. Like that would be one thing to compute. Maybe I should not put X here. X can be corrected. For example, just to give an example, we could take total momentum computed and we could subtract from it. It will be the impulse, linear impulse.
P of mu again, right?
P of mu.
See, if this is sum overall. I mean, this is a total momentum. right?
Yeah, total momentum.
Presumably that should be conserved, so at least in flat space, right?
Yeah, so thank you. Let me take one particle.
Okay.
Yeah, one of the particles, yes,
Okay.
exactly. As a pixel. No, otherwise, of course, it may not be conserved if you are only looking at particles, because beyond some order in coupling, some photon momentum will go in, some momentum will go into photons.
Right.
Okay. But anyway, it doesn't. Yeah, right. We could fix one particle, and then we will have psi and. So this is one example, but you could look at angular momentum, anything.
Okay.
Or you could look at the distribution of energy in the sphere.
Yeah, you could look at actually that's exactly the jet. You could look at distribution of energy exactly on the sphere. And and now the statement is this is of course divergent, but as KMOC have argued, although they have no proof, that when you do this and you take a, which I will define, there is a suitable classical limit. I will explain this in a minute what they mean by this. So if I'm doing impulse just for concreteness, then this is exactly the limit they show. And this. And this quantity will match with, as they show, that this matches with the linear impulse that you compute in the classical scattering process, where you start with two particles with impact parameter B. So this is I'm giving one example, but the claim is that
This is the classical impulse.
this is classical linear impulse.
What does that mean? You have the scattering.
So
Oh.
yeah. So the point is, what does this classical limit mean? That I'm going to explain in a minute. So what they say is that there is a clever way to take a classical limit inside the loop integrals of S, such that when you take this difference, you get the classical answer. Now, what is interesting is that at intermediate step, there are higher divergences here in this computation. But in the end, when you take this limit, you get something which is infinitely finite. And so far, all observables people have looked at, somehow it is happening that the procedure leads to well-defined classical answers. Like no one has found a counter example that higher divergences prevails in this limit. So this is one. Just wanted to make.
Just so I completely make sure, instead of two photons coming in and say electrons, suppose you just had, for example, two electrons coming.
Yeah, actually, this example, sorry, I should have said. This is exactly that example.
Okay, that's what seems reasonable.
Yeah.
And then you're saying, look, you could have computed the scattering classically, of course.
Yeah.
And then if you take this particular limit,
Yeah.
And the classical answers, of course, are safe.
Exactly.
And you land.
Exactly.
Is that h to the 3 by 2 h to the minus 3?
3 by 2.
I don't understand. I thought the right hand side had lots of h's. Then you bring more h's. How will you get a classical answer?
Because when you do, let me explain. So that is this. Because when we, each phase space integrals come with h bar. Let me explain.
Wait, the right hand side is a quantum element, right?
But remember that in the quantum, the higher loop go with each loop come with one. If you explicitly insert h bar, each loop will give you one more h bar.
Exactly. So you get more and more factors of h bar, and then you put an explicit h bar to the 3 by 2 out.
Right.
So then it will just go to 0 if you take h bar to 0.
No. It will exactly.
Okay.
It will exactly. So let's do it tree level, and then that will, let's take S to be tree level matrix, and so let's just look at that computation. So what we have is integral. So let me write down this thing exactly. So what we have is some this will be some actually let me write the final answer. Then I will write, it will be easy for me to. So, let's switch to tree level. In the tree level, we will have. I'm just writing tree level two F matrix between electron proton. So this is ensuring that you started with two Gaussians, two on-shell particles described as Gaussian. They scatter with some momentum. Let's say they exchange quantum momentum q. So this is p1 plus q, p2 plus q. And then, but these are coherent states again, so they are also localized on-shell.
Sorry, the right hand side was just single photon scattering, right?
This one?
Yeah.
So S can be anything. See,
Yes.
S
So you're in sign and sign.
Sine side or just electron, two electrons.
One photon of it, one electron.
Two electrons.
And not a coherent state of electrons.
No, only packets. No, not coherent states of electrons. No.
Just one. Yeah.
Yeah, exactly. So this came with momentum P1, P2, and they scatter with momentum P1 plus Q, P2 minus Q, and then we do we have to trace over all Qs. So that these are also on-shell. So that on-shell condition is here.
Okay.
And now, let's see how many powers of H bar we have. So so now, okay, let me first describe what. So far, I have not done any classical limit computation. I just literally computed this at tree level. So this P mu is basically replaced by the exchange momentum Q mu in the quantum theory. And now the classical limit is the following: that all massless momenta should be scaled with H bar.
Alright.
That's their prescription.
Very strange classical limit. I would have thought the classical limit that the amplitude of the wave we scale like one over square.
So this motivation from this comes from the fact that if you take exchange momentum going with H bar, which means that the exchange momentum goes 0, which means impact parameter is becoming large.
Okay.
So that is large, so that's the classical limit, that your particles are, it's a classical process because the impact parameter is very, very large.
Which means that they're hardly affecting each other.
Yeah, there is very little deviation. That's why perturbative theory is, you can use it to compute the what is observables. So this will not work if you have collision.
I see.
Yeah. So so this is the limit, just to say, used by this recent works of Vacuua and Roy et al, where they use this KMOC idea to compute correction to post-Newtonian, higher order correction to post-Newtonian in the scattering black hole.
Okay, so that's once again you're very far from the black.
Very far from the black hole.
I see.
Yeah.
I see. And now I understand.
Yeah. So now if you look at scaling, because this will have 1 by h bar square, 1 by h bar square, and maybe I still made a mistake. Let's see. So this is h bar. This is h bar to the 4. And there should be the coupling, right? So coupling is e square. And each coupling goes is 1 by square root h bar. So this thing will go with 1 by h bar. So we have h bar. We have h bar to the 4 here. We have 1 by h bar square here. There is 1 h bar here. And there is 1 by h bar square. And so then we have, I don't know why I wrote 3 half, e square, right? So this is h bar square. This is 1 by h bar. So this is 1 by h bar. Okay, sorry, h bar 4. So this cancel. And this is 1 by h bar. This is h bar and this is 1 by h bar. So this cancel. Sorry, actually here there is nothing. I apologize. It is just h bar to the 0. This limit. Yeah. So this is the counting, but I just So this is the.
I see. And the point is that the higher order loops, because you've put sort of more momentum in.
Yes.
There are extra powers of 1 by h bar because of these more momenta, the extra powers of h bar from the loops, and they cancel out.
Exactly. So whatever scaling we derived it for tree level, but it should be true to any exactly what you say for any node.
It feels more intuitive to me in gravity because their higher momentum means more coupling.
Yes.
It feels a bit odd here. That why is higher momentum more coupling?
Higher momentum, you're saying that if you put loop.
See, I want to see that a 2-loop graph comes with an extra factor of 1 over h bar square.
Yes.
Because you scale your momenta large. Right? Otherwise it wouldn't contribute.
Exactly.
Okay, now in gravity it's sort of clear, right? Because you're making your momenta larger.
Yes.
So all coupling constants are becoming larger.
Yes.
So at least that there's going to be some 1 over h bar.
But here also, you're right. So here also we are using this dimension of the coupling which is 1 by square root h bar. Is that the thing?
Oh, is that?
Yeah. So it's the same. That's the same reason. Every time you add a loop, you add 1 powers of inverse of h bar.
I see.
But I mean, every loop, if you count the H bars correctly, will have additional H bars, right? And then the massless particles,
Yeah,
even inside the loop, you're going to count with H bars.
exactly. Because we know that if you're massless particle, then it's not that the higher loops are quantum.
Yeah.
There are cancellations like in form factors, for example. So this is a prescription to do it very systematically.
But the point is that in the external momenta,
Yeah.
you've got some H bars.
Exactly.
So the counting becomes now more complicated.
Yes, exactly.
But suppose I just did electron, the way I'm understanding,
Yeah.
I have two lumps of electrons. I keep them far apart.
Yeah.
So first of all, they're not coming very close classically. Classically, the lumps would have had
Yeah.
some
Their
medium time.
deflection is small.
Very small, right?
Yeah.
And then all the external momenta are for these electrons.
Exactly.
And they are never becoming, they are not massless particles.
No, but they're exchanging small momentum.
The exchange virtual
Exactly.
guys,
Exactly.
the exchange virtual guys are becoming small.
Exactly.
T is becoming like order.
Exactly.
Yeah, that is right.
Okay. So somehow that gives
Exactly.
extra powers of 1 by H.
Exactly.
The fact that you're computing this not at S and T is L6, but T is K.
One by two.
But I'm just saying that he's taking, if I'm right, just
Yeah.
to understand, all the exchange guys are massless, right?
Yeah.
So the fact that you have a small denominator is being taken into account by scaling the H.
But how small?
How small? Exactly.
The how small is set by T in the
Exactly.
three-level graph. So now if you take T to be order H bar, that 1 over T pole will become 1 over H.
Yes. I agree.
And that will cancel out.
Yeah. So if you're basically saying that these loops are quantum, but because your wavelength of the massless particle can become arbitrarily large, they can contribute to the classical. So you are taking exactly.
Sorry, maybe I was okay. Yeah. Anyway, okay. This is the counting, and then the loops will contribute. Right? In general.
Exactly. Yeah.
Okay.
So they just made it. I mean, this is not new. I mean, this is people knew, of course, that I think massless, we have massless propagating particles, loops contributing classical limit, but they gave an algorithm of how to do it. And what is one of the interesting things which is not completely understood in the derivation is why this come out to be infrared finite. I mean, they are classical, fine, but why should the
And once again, you're computing just these ladder graphs, right? Effectively, the things that will contribute will be these ladders and cross lines, or not?
more than so in the case of say if we went to one loop, for example, then we would also have a graph which is so this is the incoming, and this is the
For a moment, if we work with fermions, would it be only? I mean, this is part of sort of the force exchange for scale.
exactly.
If we work with fermions.
Oh, then only this is for scalar. Yeah, exactly.
Yeah. Okay. So then makes sense.
Yeah. It's very iconal.
Yeah.
As you would say, right? Yeah. Okay, so these are one class of observables, and these are the ones which are defined without any making any delta resolution scale of detector or anything like that. It's just that but they are not quantum.
I'm roughly understanding in this language that every time I get a one of these ladders gives me an extra 1 over T.
Precisely.
Roughly speaking.
Yes.
And so if we get lots of 1 over T's, that cancels the lots of loops.
Exactly.
And these will be the only graphs that will cancel those ones.
Exactly. So anything that, and also of course you're right. So you get 1 by T. In principle, you get some numerators, and if the numerators, if you expand in H bar, only the leading term, which will literally give you 1 by T, as you said, will continue.
Fine.
Yes. Okay, so these are the KMOC observables, which are of different kind. I just wanted to emphasize because they don't depend on the thinking of QED as an open system. And there is another, finally, one observable.
Sorry, just what is KM?
Oh, I should have said that. I apologize.
No.
I'm sorry,
No.
constantly interrupt, but there's another classical limit, which would be to take scattering of coherent states.
Literally, you're saying infinite. Think of the but for the if you, for field it's okay. But
For bosons, maybe.
For bosons.
Yeah. Okay.
But for electron, I mean, I'm just thinking of a classical particle with charge, or let's say,
Yeah.
then
But
it's a wave packet, right? Only.
because that's one thing you could do. But there's another thing you could do, which is actually make a coherent state, which would really be a classical lump of the scale.
So many particles.
E to the power a diagram, zeta a diagram on vacuum.
Okay.
Okay.
So yeah.
That should also give the same answer.
But just I mean, so I agree that if you are looking at a scattering of say gravitational field or something, and for the field you have to do the coherent state of gravitons.
Yes.
But if I look at two black hole scattering, each black hole think of it as a scalar particle, then why would it will just be a wave packet for the trajectory of that particle, no? Like
No, he's saying take a classical wave in the phi theory.
in the particle theory, massive particle theory.
Yeah, let's say they're scalars.
Yes.
So you take two waves of those scalars and they come, maybe they stay far apart. Then each generates a field under which the other scatters. That's the classical limit.
Yes. But it's not same as because you are putting in the A diagram you are saying.
That would amount to scaling the amplitude, like 1 by square root h bar.
But
Because the number.
no, please.
No, I'm saying the number in a coherent state, the number of photons that you excite is sort of like 1 by square root h bar.
Exactly.
But not necessarily in scaling the momentum.
Oh, that's what I want.
Yes, okay. It's a number. It's a number that it's coming from the coherent nature of
It's
it.
coming from the number of particles.
Yes.
I was just wondering if you could see that both these give the same graphs. Sorry.
No, but I think even there,
No, I
correct me, you might have to match with the classical limit, you might have to keep the transferred momentum span.
Yeah.
not necessarily actually there. So actually there is okay. I mean, as a side comment, I mean,
Some limit.
yeah.
You should just get it even non-linearly the classical answer.
Yeah. So I actually there is an example of the type you are mentioning, Shira. So when Ashok and I looked at the classical soft theorem from the quantum soft theorem, this is the way we did it. That we look at a process where you have large number of quantum, let's say gravitons being emitted,
Right, exactly.
and then we take a large, then we do a saddle interval,
Yes.
and we get the classical limit. And this works even without large impact parameter. Yeah.
Right.
Yeah. So this is the
Because you just reproduce the non-linear classical data, right? I mean,
And reproduce the non-linear, but I was wondering whether if your virtual time scales become of order h bar, then that would.
no, that would be so. You need
It has to be kept fixed. Momentum has to be kept fixed, but they don't have to be scaled like 1 by.
Exactly. See, you can either have large impact parameter or you can have a extreme mass ratio type where you have a small parameter, like the ratio of two masses is very small. So that the amount of energy emitted is not significant, which is same as small deflection.
But maybe it's trivial, but I was just wondering whether you could see that it should be the same part of the same integrals of the quantum amplitude that contribute to both elements, right? Because both should give you classical answers.
That's an interesting point because they look very different. I think one has to investigate this.
Yeah.
You are right, I agree. But it should turn out like that, but okay. But of course, the one you are mentioning, the other approach you're mentioning, that not been really used that much for these kind of observations. So one should look at it actually.
I don't know if it's interesting or not.
No, but yeah.
Just if you said classical limit, that's the first thing I would think about.
Yeah, that's how actually we did the, Okay.
Even if you make
Yeah.
lots of like the classical, I mean, how do you make sure that this process is
No. This Q integral is just our usual integral, yeah.
The limitation.
Okay, so now I'll give you one final example of the observable, which will be the main object for us going forward, which is called semi-inclusive cross section. And this was introduced to me by Ashok because this is something that he used in the string amplitude computation. So I'll just give you a brief idea of what this cross section is. So here the point is the following. So let's again look at our process only. So we tell me when I have to stop, huh? Tell me when I have to stop. After this maybe it's
1 o'clock.
1 o'clock. So now let's say that we look at a process like this where we have two photons coming and scattering into two electrons, but we say that the momenta in the initial photons is larger than, is equal to P1 plus P2 plus some momentum which is lost. And the only constraint we put for simplicity on Px, this is just for just to explain this idea, is that Px square, I mean, the invariant should be less than, say, mass of the electrons. So what I mean by this is that you can have arbitrary number of photons just being lost, but it is not, it's just that you have a process in which stuff is happening, where you can have photons with finite momentum, which are also being emitted. So everything is, all the momenta are sharply defined, we are not compromising on anything. We are just saying that let's just look at this process where two photons go into two electrons and lot of photons. These photons can have soft photons, hard photons, anything. Now you can look at the following observable, which is similar structurally to this sufficient inclusive, but conceptually a bit different, is that you sum over all x. So that's it. This x may not be soft photon. They can be soft, hard, anything. You just do this. So you are only interested in, you are ignorant about your photons in the outgoing state, for example.
You're keeping track only of charge particles.
You are only keeping track of some states, exactly. In this case, only charge particles.
The detectors just don't detect.
Yes, exactly. And now you can show that, which I will show maybe in the next lecture, that even with the usual S matrix, and that is not very surprising, because even when the x had only soft, Weinberg showed this is infrared finite, so not surprising. If you include hard also, why should it be high divergent? And okay, you can check that this thing is infrared finite. And this one is, so this is called semi-inclusive cross section, and this one is, it's only, it's really only function of, the momentum. So it's an interesting observable in that sense.
Sorry, just say one small
Yes.
thing. So Px are the photons or whatever are what? The soft?
Not soft, not soft. No, not even potentially soft.
Okay.
Yeah.
So what is Px?
So you have a process in which two photons can give electrons and photons, but we only want to keep track of electrons. So this is a cross section.
Yes, refers to photons.
Photons. I mean, this for simplicity, because I am assuming that the momentum lost is less than enough to create an electron. In principle, I could keep some electron, but then I have to be careful about how I am keeping track of two electrons and not the others or something. So just to simplify, I just said only photons.
Okay, so say photons.
Yeah.
We just don't give some overall percentage.
Exactly. Exactly. And this is a nice thing. I mean, so and one can
I mean, this more or less has to work for me.
more or less has to work because of Weinberg's analysis.
But then you may as well say that you're just not keeping track of the soft photons. I mean, if you're going to not keep track of something,
Yeah.
you didn't like not keeping track of the soft photons, right? Earlier.
Yeah.
I think
Why is this
sensitive?
Yes, exactly. The advantage is pi square is Lorentz invariant.
This requires figure.
Yes. So one test that we will make from the infrared finite S matrix is to ask. So you compute this with the standard divergent S matrix, and you get some finite quantity. And this is our concrete data point in there for the next talk also, that whatever S matrix you propose to me, which is manifestly infrared finite, I should check that if I compute this observable, it should match exactly with this answer. So this whatever progress we have made, I will report on that in the next. So anyway, so these are some of the observables. So this is a very bizarre situation in theory, gauge theory and gravity, where no S matrix but many observables that we built out of S matrix. So yeah, so maybe I can start with the coolish second point, or we can take questions also.
Just to ask you, I mean, was there something common about all the observables you finally constructed?
Except the KMO ones were a bit different.
And there also, you're saying no, there was no fine coarse graining?
No.
There is only.
But there is a coarse graining of the
Of measuring only a single trace.
Yeah. Yeah.
You're measuring.
No, measuring only one
Thing, exactly. That coarse graining of that sort is there. But what I mentioned those observables because they are used a lot these days, and also because it is not clear why classical limit doesn't have higher divergence. If you look at the computations in general, there are cancellations that happen between different higher divergence. Yeah.
Sorry, but I thought the way you said it, that classical calculation would ultimately just amount to trajectories being bent by long range forces.
That is what they, in the end.
Therefore, it would be.
But it's not a theorem. It's an algorithm. It's a proposal that it produces for you classical observables. Right? It's not like a systematic derivation of classical limit.
Yeah, what you're saying is that this particular h bar going to zero limit.
This scaling, yeah.
That it gives you the classical limit.
For all the observables that we have looked at so far, it gives.
But it's not a theorem.
It's not a theorem. No. It's like, I think it's if you look at the argument, it's kind of argument Shiraz now mentioned about the iconal, etc. It's based on those intuitions. Yeah.
It's so subtle to define the classical limit. There should be a h bar going to zero.
Yeah, certainly. I mean, we could always ask as an independent question why we look at these things. The reason this is useful is because I mean, naively it looks like we are doing some roundabout thing. We are first going to quantum, going to classical. But the advantage we get is we are taking classical limit as early as possible in our computation of the S matrix. And that combined with the fact that we have so much progress in computing amplitudes, that gives us a leverage. We are really not doing full quantum amplitude and taking class. That would defeat the purpose, of course. Yeah. Yeah.
Okay, mostly if you consider the angular momentum.
Yes.
Then what is that is also.
Well, if you give the same answer, we will get, which is log t, right?
Log.
But it's not divergence coming from the S matrix, right?
Yeah.
Yeah. So
But that log is
it certainly will show exactly. It's exactly the same.
Sorry, this KMOC is sort of like a hybrid, right?
Hybrid.
The initial state is sort of fine-grained,
Yes.
but the final state is
You are
coarse-grained.
tracing over. Yeah, exactly.
But if we just make both initial and final state coarse-grained, then even quantum level it will be IR fine.
Oh, sorry to interrupt. Why this one? I
Yeah.
don't understand. Why is there a final state coarse grain and this?
Because you're only keeping track of the energy of the final state, not anything else.
I mean, you're tracing over all the phase space cues.
Keeping the whole trajectory, momentum information.
No. Yeah, go on.
Not useless.
Yeah, I mean, you're basically what you're saying is that I think what she is saying is correct. So what I understand about KMOC is that you start with P1, P2, which is not much coarse grain, you have a wave packet, and then it scatters, and it could give you any momentum P1 prime, P2 prime. You trace over all P1 prime, P2 prime, such that they are on shell and momentum conservation is satisfied.
Oh, you are tracing.
Or you keep track of some gauge variable.
I mean, module, yeah, of course, yeah.
Why don't you, if you're taking, at least in the classical, if you take the classical limit, you just compute where your wave packets are.
Yeah, so you could think of it like that when you coarse grain, this will peak around the classical value, in the classical limit.
Coarse graining, sorry, you just mean you fold it into the wave packet form.
No.
In his definition, he had an operator. Could you write
Yeah.
I'm sorry, I missed this part.
It's like computing a 1.5.
Yeah.
Exactly, just computing 1 point.
There was some O, right?
That is here.
That is your O. But more generally, there's some O.
Yeah.
That's it.
O, which is a function of P1, P2, Q1, Q, and Q.
A4, right? A4 stop.
No, this is only A4. Because we are computing expectation value.
There's S back.
Yeah. So, you are right. So this is, I was doing estimate, this was tree level. So at tree level, only one is content. Because it's, you write S as 1 plus IT. And so the leading contribution is commutator of T. Sorry, I didn't, yeah. You get this. So I'm writing this contribution because tree level only this is there. Exactly as you're saying at loop, you will also have the contribution coming from.
So something, I mean, what they're doing is sending in, they're giving in detailed information of what they're sending, but they're only measuring, let's say, the profile of the stress tensor of what comes out.
Yes,
Throwing away other information.
yes,
So in
exactly.
that sense, what comes out is coarse grain.
I see, but it seems unnecessary. I mean, if the central physics is you can take a good classical.
It helps them.
I know nothing about the subject.
No. It helps in the following sense that you want to compute this 1 point function as Sonkar said up to some arbitrary order in, for example, in the velocity expansion. So that's what you want to compute. Say you're doing post-Newtonian physics in gravity. Then this helps in the sense that if you know this at very high loop orders, which is what we are able to do now using new techniques, it helps you compute these things. So it's necessary as a technical tool.
But I was wondering something goes the other way, which is that if we replace the initial states by also coarse grain, meaning created by gauge invariant operators, Okay, then it will be for IR finite even at the quantum.
You're saying that
If we do the Onkar's favorite thing, that is, you make the initial state by some Euclidean path integral with some trace of it,
Yes.
even in n equals 4 angles.
yes.
Then this will be manifestly IR finite because what you're doing is computing some convolution of correlation function
Okay, I see.
of Gaussian variant operators, which will be cool.
But that would not give us what we asked here from the
It
table.
may not be.
But it's a different observable. It's a different.
What is it? Sorry, I didn't understand your observation.
Yeah, I'm saying create the state also by what you're measuring of the state is some Gaussian variant operator. So suppose we also create the state with Gaussian variants. Okay,
Yeah.
if we do that, then there should be even at the quantum level no IR.
Yeah, no higher. Yeah. Even at the quantum level, before h bar going to 0.
Yes, I agree.
Exactly. And I said
It's actually minus n Hoffman, I think.
Yes, yes.
This is roughly that point, right? That even at the quantum level, that observable is completely well.
yes.
No, you're just saying that if I just created say the initial photons out of gray sets,
Yes,
I can do.
which you can do.
And
You create some state out of trace S square or in n equals 1.
but if you wanted to create fermions that way, you have to attach Wilson loops in your
Or psi bar del psi.
local fermion.
Yeah, then this is the problem.
Yeah, because
The
therefore
problem is Gaussian variant observables don't really allow you to create charge particles.
Exactly.
That's the root problem, right?
That is the problem.
So I thought the root problem here is that once you have charged particles,
Yes.
then you don't have good asymptotic states. Then
Exactly.
either you put your Wilson lines, which hopefully
Exactly.
will cure it,
Exactly.
or you won't,
But
right?
you might hope that you create a pair of charge particles and they separate
Yeah.
and do your effective thing.
You could You could do a Wilson line between them.
Or even create them with a local operator.
Yeah.
And let evolution take over.
Yeah.
At some point, there'll be some part of the wave packet that goes, one guy goes here, one guy goes here. They do their own thing.
Yeah.
But this is what Malthus and Hoffman.
Yes, I agree completely. Agree. Yes.
Right?
Yes.
How do they? I mean, it's hard to do.
All they're doing is this. They're computing the as Onkar said, 1 point function of the stress tensor as a function of sphere variables.
Yes.
In various different states.
Yes.
In states created by acting on the vacuum with, let's say, stress tensor.
Yes.
So here we are very far from estimate.
And then from there, you want to
Actually, we are not that far from
extract the
extracting
scatter. I mean, it seems probably you can do it, but
They treat this as the replacement to scattering.
Yes.
Because it's a well-defined thing, measuring what comes out from what goes in.
And now actually people have connected. I think even
the statement of unit.
this with the S matrix.
No statement because it's cost.
Cost gradient.
Yeah.
Okay. Yeah, if you just want to compute, so let me paraphrase, please correct me. You say just compute instead of in states in terms of a single particle or representations of the Lorentz group, I just take Gaussian variant operators hitting the vacuum in states. I create out states, I get something well defined. Sure enough. But I thought the thing you guys want is a fine grained thing which is, has the properties of a S matrix.
Yeah. So this goes the opposite direction. It makes it completely well defined by completely giving up fine grain.
Yeah.
It's not far from what you would do in gravity. I mean, the bulk field. Because the single trace operators are the incoming outgoing gravities.
Yes.
Except
What is the LSC? How do you make sure that the stuff that generates is on shelf? For scattering, you want that representation, right?
yeah, no, their point in Malthus and Hoffman is that trying to do that in conformality theories
Yes.
is a fool's game.
Yes.
So you just do what you can, which is transition amplitude.
Transition amplitude between operator insertion.
Operator insertion. That's all.
So again, I mean, how does this correct? How is it connected to some scattering that you
No, it is connected. I think now if people have looked at transcription of these into, so for example, one thing that these are called gravitational event shapes. So idea, I think what people, you scatter some states coming from scribe, and then you compute exactly what I think unconventional are the same. Like take the stress tensor operator localized at a point.
Yeah.
This is this Cordova type, where this is integral du n hat.
Exactly. The same question arises in QC. You scatter two mesons, let's say, and then you get some stuff out.
Yeah.
How is this connected to scattering of quarks and gluons?
Yeah.
It's the same
It's
question.
very elaborate.
It's a very elaborate.
And it's non-trivial. And so, okay, I don't know what the aim is. If you all just want Gaussian variant operators.
No, she is giving an example of observables which without even the h bar limit will be higher finite.
Yeah.
Which these are not.
Yeah, interesting or not, I don't know. Maldas and all were able to use it to prove theorems about performance, right? But it was about.
Yeah. No, I think even recent, I think these ones are now, people are looking at them now in the, through direct bulk computation. I think Giboido also has some paper recently on these gravitational gradient shapes. So, yeah.
Okay, just to understand, I mean, is it more or less obvious, or does it require proof which has been given that as long as instead of asymptotic in and out states as we define or try to define this guidedly perhaps in LSZ formalism, we just have gauge invariant operators, everything is infrared.
So I think it's more or less obvious because you get it from convoluting correlation functions of the gauge invariant operators. Whose form you do? And you can just get
QCD, are you sure that?
not as QCD, N equals 40. Confirm it.
Okay, but in QCD, we will
I
not
think
stick-
QCD
is
will
it
also
obvious? Is it obvious?
Seems right? Because all it will be is LSM for the physical parts. It will be LSM for the glue balls and these ones.
Yeah, in fact, for QCD, they were studied before.
So you would
Uh,
have the
So it's clear that if you just had gauge invariant operators,
Yes. Yeah, event shapes, what
Factorize on the
Salman and I have shown that they are IR finite observable QCD. Exactly this way.
this time. So then, what is it that one is trying to prove in this whole game? It's
So again, so we have so many IRCF observables at different with different inputs. For example, coarse grain state, either classical limit or a detector resolution scale, etc. But what is the underlying object which is computing these things? I mean, this means there may be some.
I mean, at a zeroing or a conceptual level, I would just say the underlying object is gauge invariant correlators. The non-trivial issue is to extract what you see in experiment by scattering electrons out of that.
No, but
Isn't that the? I mean,
but for example, the cross section. The semi-inclusive cross section, for example, right? I mean, these ones are.
I mean, it would be sort of interesting. The following thing would be sort of interesting, right? We could do what we do in QCD.
Yeah.
That is to think of these as, what are they called? Parton distribution function. The operators create a Parton distribution function. Then the partons scatter.
Yes.
And then you get,
Yes, sure.
once again, you get some Parton distribution.
then you fragment.
Then you fragment. And then in that process,
Yes.
all the divergences in the S matrix
Yes.
cancel with the divergences in
The-
the Parton distribution function.
Or the fragment.
Yeah.
Yes, exactly.
So, through that route, this might help you understand
That is Schwartz.
elements of the.
That's Schwartz
Yeah.
anecdotes. That's Schwartz anecdotes analysis. That the point is that so one way to understand that cancellation that you talk about is in this become very manifest in the soft collinear effective theory. We will see.
Okay.
So that is the input they have used.
Just along the lines of Shiraz was saying, at least, I'm sorry,
No.
in the epsilon work I did on fragmentation and so on, it was the case.
Yes.
There were a lot of results also.
Yes.
That you could move the
Yes.
divergences around, but finally, you could logarithmically.
Exactly. Yeah.
and they would
Exactly.
answer
Exactly.
Beautifully. I don't know the status of that, but at least QCD scattering phrased that way.
Yeah.
I mean, at least a lot of the infrared divergences went away, right?
Absolutely.
I don't know if there was a proof.
Yeah. I think I would say that the conceptual confusion becomes more robust as more observables you produce it at IRCF. Because it kind of tells us that there may be a fundamental object which must be well defined, which is giving us all these observables. And I mean, right now the situation seems to be that the S matrix, which is the central object in all this computation, is fixed. But these observables are IR finite through various cancellations with other ingredients, right? So that's the question.
That's the key question.
That's a key question.
The S matrix as thought of for asymptotic states which cannot be created out of gauge invariant operators.
Yes, yeah, exactly.
That is the key question.
And of course, now as I was mentioning, I think maybe I don't know how much time I will have. What Kulish turned the problem. They said that well, actually, forget IR divergence. The way we define S matrix in QD itself is problematic because we are assuming states are free.
Yeah.
So suppose we don't know S matrix IR divergent, but we just follow our procedure to define S matrix the way we would do.
Yeah.
Then what we get? What is that S matrix? And if that's IR finite, well and good.
Yeah, and just one more comment. It's, the hope might be this, that in QCD you can't hope for anything. It's just gone. Because there's nothing, no asymptotic states other than what you see. But maybe in a conformal there are asymptotic waves. They don't settle down, but they're there.
So n equals 4.
N equals 4, right? You set the gluon. The problem is that will decay into two gluons. And the two gluons will decay into two more, and it'll never end because long times
Exactly.
short times because of conformal invariance, right? So maybe the hope is that if you use the correct states, the correct asymptotic states, both the Parton distribution functions and the X matrix
Exactly.
are finite. You can work with completely finite things.
Yeah, this is the hook. This is precisely the hook. Yeah.
Yeah, and that would be very cool, right?
Yeah, yeah.
The text would be for these
Yes, yes.
inclusive type.
Yes, yes. This is exactly what we are attempting for the semi-inclusive infinity. So I will tell you how far we reach.
So you say it again, the Parton distribution functions, the fraction functions are all finite.
Let's see, they're not finite when you work in terms of gluons.
Yeah.
But suppose you can define a shower state.
Exactly.
Something where it's an eigenstate which is one gluon that goes to two that goes to some other state. In terms of the shower state,
Yes.
both the Parton distribution functions and the S matrix is finite. The S matrix is unitary, and then you don't need to work with these
Yes.
inclusive things. You
Yes.
just work with this one.
Yes.
That would be a dream.
Yes. Yes. Yes.
Would be
Yeah.
fantastic.
That's the ultimate. I mean, that's the dream.
This is here you assume that there exists some asymptotic states. It could be that these shower states are never asymptotic either. Does there exist some state which is asymptotic because they keep on interacting?
Yes.
Every-
Yes. Yeah.
But it's possible you can diagonalize that tree. This was with this,
No,
Yeah.
but it has to have the feature that is not interacting with this shower state.
with that shower state, exactly. It has to have that feature. It's not clear.
Yeah.
This is a dream. That's why it's a dream. Yeah. I mean, in n equals 4. I suppose in QE, massive QE, you can prove it. Right? That sounds almost clear because at long distances, these are free. These showers are free. The
Yeah.
photons don't interact with each other.
Yeah.
So the asymptotic QED sounds like it's very likely to use it.
More rigorous.
Yeah.
Okay, what
But unfortunately, there are issues.
asymptotic
Asymptotic meaning, not asymptotic, massive.
where all the charged particles are massive.
All charged particles are massive. So at low energies, we've just got pure QE, pure Maxwell theory, which is free. So there, the showers are pretty trivial.
Yes.
They're not
Schwarz type definition, right?
Yeah.
So, okay, so what is the ring that
Yeah.
you take massive,
Exactly.
say scalar or fermi or whatever, QED, and you want to define asymptotic states.
You want to find new asymptotic states, in terms of which scattering will be finite and
Yeah.
unitary.
Yes.
Yes, that is it.
Yes. Yes.
Why not? I would just say, look, your asymptotic state is a Wilson line from infinity to. You didn't put it in, You just set up a problem and I'm just.
That's what we are heading.
So that's the natural thing, right? Okay, you didn't set up a gauge invariant problem. The theory is clever enough. It told you I'm not going to give you a good answer.
Yeah.
Set it up. That's the answer to Shiraz's question. Why? What is
Well, I
that?
mean, so there are two different things. No, yeah.
This is the question.
So okay, just once massive QED. Suppose I were to say this. Okay. You won't like it,
I
obviously.
would like it. Yeah, where are you taking this Wilson line to?
And I'll say it doesn't matter. You have to take it to infinity. It doesn't matter.
It doesn't matter, but not even,
I mean, I would
Not
take
at
it
all.
where the world line, every instant.
That is exactly how this will turn out. Exactly what you are saying will turn out here.
Okay, so
But it's something sound.
No,
No, you are not.
You are
No. Kukulish Pradeep told us where the problem lies and how to define these jets. And then soft collinear people told us how these jets are precisely the Wilson line along the world line of the charged particle. So it will give you exactly the result that you want. So it all ties together in QED. But there are issues, technical issues defining these jets. You get new UV singularities that are a bit problematic. So we will come to this. Maybe let me.
It's not
I don't know.
clear. These are easy to work with and all.
Yeah.
Maybe you had in mind something more local.
I wanted something local because I felt that then you change the shape of this and you get different answers. But maybe not.
Yeah, I mean these are one interesting thing is that these are really never a single electron can be. I mean, once you go to the dressing, because of the fact that dressing also it's not only you're not only dressing it by radiated photons, like you are also dressing by whatever soft photons are there in your system. So these Coolidge Pradeep states are not. We cannot think of a tensor product of single particle state. They are just really composite states out of whatever charged particles and which makes the analysis a bit complicated. But we will see that. I mean, that will just come out of the competition. So there could be a better dress state. I think Shiraz is saying there could be a better dress state,
Yeah.
which is separated, really separated.
Yeah.
But then the problem is in the S matrix, we know there's a Coulomb divergence. And naively not clear why that should go away if we don't include that in the dressing. right? So that would still remain a problem. But at the level of cross section, what you are saying is that look at mod A square. You will be happy if this is IR finite, even if A is not IR finite. Right? That will be an upgrade over the current scenario, right? That's what you are saying, I think. Like you are happy with the divergent phase because that doesn't appear even in the cross section.
But will it appear in SS dagger is equal to 1?
Then it will appear. Yeah, I mean, I would think so. When you insert states, each term will have higher divergence.
Then I'm not.
Because that phase will depend on this. It's not a universal phase. It is, right?
Yeah, it depends on the momentum.
Even producing this kind of understanding that asymptotics in general conform field theory, you have pairwise interaction, as opposed to some all point interaction. That
Yeah.
would also be,
Now, this pairwise comes from gauge invariance, right?
No, I mean just in conform field theory because you're going far away.
I see.
The way this things work.
Yeah, let's say it's towards saying that maybe you can have something better than unwieldy Wilson lines.
Not
Just
perhaps
something-
still the thing that Shiraz wants, but at least as good as this.
Or maybe just Wilson lines between guys or something. I don't know.
No, that's nice.
Yeah, which is
I
nice.
also have to choose up to take.
I know.
Yeah.
Maybe.
Yeah.
So, tell me where I should stop. Should I stop here?
This is good. But it's been great. I mean,
Okay.